Welcome everyone to the 2026 Vision Spectra Inspection Summit. Thank you all so much for joining us, and in this session you'll hear from Thomas Brucolacchio, the CEO, CTO, and co-founder of Innovations in Optics Inc. Thomas earned his doctorate in electrical engineering, currently holds more than 80 US patents, and is recognized for his work in high brightness LED illumination, optical system design, and the development of engineered light sources. Today he joins us to review recent developments in high radiance, solid state illumination for industrial inspection. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's sessions, you can always come back later and watch them on demand. That's all for me. Thomas, it's great to see you, and we appreciate you for taking the time to join us here at the Inspection Summit.
Well, thank you. I'd like to thank you, Jake, and all the staff at Photonics Media for hosting the webinar, along with my colleagues at Innovations in Optics. With a special thanks to Karen Allardyce, Business Development and Applications Engineer, for her significant contributions. Today, I'd like to discuss how advances in high radiance LED illumination are helping drive the next generation of machine vision systems. As inspection requirements continue to evolve, illumination is no longer simply an accessory to the camera. It's become an integral part of the imaging system itself. We'll look at several different machine vision architectures, including structured light for three-dimensional imaging, multispectral and hyperspectral inspection, and emerging applications extending from the ultraviolet through the shortwave infrared, often referred to as SWIR. Throughout the presentation, I'll focus on engineering principles behind these illumination systems and explain why radiance, spectral control, uniformity, and optical efficiency have become increasingly important for achieving high speed, high accuracy inspection. Before discussing the technology, I'd like to take a brief moment to introduce our company. Many of the examples I'll discuss today are drawn from engineering challenges we've encountered while developing advanced illumination systems. So let me briefly introduce Innovations in Optics. IOI was founded in 1993 and specializes in the development of high power solid state illumination systems for demanding industrial, biomedical, analytical, and scientific applications. Over the past 3 decades, we've developed a broad portfolio of technologies involving LEDs, VCSELs, optical coupling, electronic control, thermal management systems, and high radiance illumination platforms. These innovations are protected by an extensive array of intellectual property portfolio and have been incorporated into products serving markets ranging from semiconductor manufacturing and machine vision to biomedical imaging and solar simulation. Our headquarters is located just outside Boston, where optical, electrical, mechanical, and software engineering are all integrated with prototype development, a Class 1000 clean room, and production manufacturing all under one roof. This breadth of experience across multiple industries has provided valuable insight into the illumination challenges we'll explore throughout today's presentation. Here's a quick roadmap for today's discussion. I'll begin by discussing why illumination has become such a critical element of modern machine vision systems. We'll then examine some of the engineering principles involved in designing high radiance LED illumination, including the factors that influence overall inspection performance. The second half of the presentation focuses on several illumination architectures developed for specific classes of applications. We'll look at structured light for three-dimensional imaging, multispectral and hyperspectral illumination, and finally review representative industrial applications together with several emerging trends that are shaping the future of machine vision. I'll conclude with a few key observations before opening the floor to questions. Let's begin by looking at why illumination is becoming increasingly important. Machine vision systems continue to evolve at an extraordinary pace. Today's cameras offer higher spatial resolution, faster frame rates, and large fields of view greater than ever before. At the same time, inspection systems are increasingly incorporating three-dimensional imaging, multispectral and hyperspectral analysis, and more recently, AI-assisted inspection algorithms. While these advances provide tremendous new capabilities, they also place much greater demands on the illumination system. Higher camera speeds require shorter exposure times, which means more photons must reach the sensor in a much shorter period of time. Larger inspection areas require illumination that remains uniform across increasingly wide fields of view. Multispectral imaging demands stable, repeatable spectral output, while synchronized pulse operation becomes essential for capturing rapidly moving objects. As a result, illumination has become one of the primary factors determining overall inspection performance. In many modern inspection systems, improvements in lighting can have as much impact on the system performance as improvements in the camera itself. That realization has driven the development of a new generation of engineered LED illumination systems, specifically optimized for machine vision. So, what characteristics define an ideal inspection illuminator? That's the question we'll address next. Before discussing specific illumination architectures, it's useful to ask a simple question. What characteristics define an ideal inspection illuminator? Every machine vision application is different, but the design objectives are remarkably consistent. First, the illumination must deliver sufficient irradiance to support short exposure times without sacrificing image quality. As production speeds increase, available exposure time decreases, making efficient light delivery increasingly important. Uniformity is equally critical. Variations in illumination across the field of view can easily be mistaken for variations in reflectance of the object itself, introducing unnecessary measurement uncertainty. Many applications also require precise spectral control. Selecting the appropriate wavelengths can significantly improve contrast between materials, reveal otherwise invisible features, or enable fluorescence and multispectral analysis. Long-term stability is another essential requirement. Both optical output and spectral characteristics must remain constant over time despite changing environmental conditions and continuous operation. Fast temporal response enables precise synchronization with cameras, allowing pulsed operation that freezes motion while maximizing available optical power. Finally, an effective illumination system should deliver all of this with high optical efficiency, long operating life, and low maintenance. These design objectives provide the framework for the engineering decisions we'll discuss throughout the remainder of the presentation. Unfortunately, conventional illumination technologies rarely satisfy all these requirements simultaneously. Historically, machine vision systems have relied on a variety of illumination technologies, each offering certain advantages but also significant limitations. Halogen lamps provide smooth, broadband spectra, but generate considerable heat, consume substantial power, and require regular replacement. Pulse xenon sources produce very high peak optical power on a microsecond scale and remain an excellent choice for certain high-speed imaging applications. However, their lifetime is relatively short, and the repetition rate is limited to the order of 100 Hz. Lasers can provide extremely high brightness and excellent temporal performance, but coherent speckle often limits image quality for many inspection applications. Conventional LED illumination solve many of these problems by offering long life, high efficiency, and reliable operation. However, standard LED systems are often limited in radiance and may not be optimized for demanding inspection geometries. Engineered LED illumination seeks to combine the strengths of these technologies while minimizing their weaknesses. By careful optimization, the optical, thermal, electrical, and mechanical designs together, it's possible to achieve high optical output, excellent spectral stability, rapid pulsing capability, long lifetime, and highly uniform illumination in a single platform. Although LEDs generally produce lower peak optical power than xenon flash lamps, they offer nanosecond to microsecond scale switching, programmable pulse widths, precise synchronization with cameras, and very high repetition rates. These capabilities make engineered LED illumination increasingly attractive for modern machine vision systems. Rather than viewing the light source as a commodity, we increasingly treat it as an engineered subsystem designed specifically for the inspection task. Of course, selecting the light source is only part of the challenge. Overall inspection performance depends on the entire optical system. Even the best illumination source cannot compensate for poor systems design. Successful machine vision systems require a careful optimization of multiple interacting parameters. For example, working distance is often dictated by mechanical constraints, Yet increasing that distance naturally reduces the intensity unless the optical system is designed to compensate. Likewise, maintaining sufficient depth of illumination allows objects with varying sizes to remain consistently illuminated without introducing excessive intensity variation. The camera imaging lens influences both light collection efficiency and image quality, while vignetting and cosine to the fourth fall off can reduce illumination towards the edges of the field of view. Signal to noise ratio ultimately determines how small a defect can be detected or how accurately a measurement can be made. Finally, selecting the proper illumination spectra often determines whether the feature of interest is visible at all. The important point is that these parameters are strongly interconnected. Improving one often influences several others, making illumination design a true systems engineering problem rather than simply selecting a brighter light source. Those interactions can be summarized in a single concept. Designing a high-performance illumination system ultimately comes down to balancing several engineering objectives simultaneously. Radiance determines how much optical power reaches the inspection target while maintaining practical working distance. Uniformity ensures that image variation originates from the object itself rather than the illumination system and maximizes camera dynamic range. Spectral control allows the illumination to be tailored to maximize contrast for a specific material or defect. Thermal management plays a central role because junction temperature directly influences optical output, wavelength stability, and long-term reliability. Fast temporal response enables precise synchronization with modern cameras and supports high-speed pulsed operation. Optical efficiency ensures that as much generated light as possible reaches the inspection target rather than being lost within the optical system. Long lifetime minimizes maintenance and improves overall system availability. Finally, every practical system must achieve the appropriate balance between performance and cost. The most successful machine vision illuminators are those in which these design objectives are optimized together rather than independently. Achieving that balance requires more than selecting an LED. It requires careful engineering of the complete optical platform, which includes the camera or the detection system. Everything we've discussed so far ultimately depends on how efficiently photons are generated, collected, and delivered to the inspection target. Modern illumination systems begin with single or multi-die LED arrays that provide the desired optical power and wavelength selection. From there, specialized optical components preserve étendue while collecting and shaping as much of the emitted light as possible. Efficient thermal management maintains stable junction temperatures, allowing the LEDs to operate at high current without sacrificing reliability or spectral consistency. Mechanical alignment is equally important. Small positional errors can significantly reduce optical efficiency, particularly when coupling into optical fibers or compact projection optics. The result is an illumination platform capable of delivering extremely high optical performance while maintaining long operating life and excellent repeatability. This engineering foundation enables the specialized illumination architectures we'll discuss next. One of the best examples is structured light, where the illumination itself becomes the measurement tool. Now that we've discussed the engineering principles behind high-performance illumination, let's look at one application where illumination becomes an active part of the measurement process. Unlike conventional two-dimensional imaging, structured light determines surface geometry by projecting a known optical pattern onto the object. One or more cameras observe how that pattern is distorted, and software reconstructs the three-dimensional surface from those distortions. This approach offers several advantages. It provides non-contact measurement, excellent repeatability, and very high accuracy while supporting rapid inspection of complex parts. Structured light has become widely used in robotic guidance, dimensional metrology, automated inspection, and reverse engineering because it can measure an entire surface much more efficiently than traditional point-by-point techniques. Importantly, the projected illumination pattern is no longer simply providing light, it becomes the reference used to calculate three-dimensional geometry. Thus, the quality of the projected pattern is critical. One implementation of structured light illumination uses a high-radiance LED projector to generate precision optical patterns. For accurate three-dimensional reconstruction, those projected patterns must remain sharp, highly uniform, and stable across the entire inspection volume. High optical output enables longer working distance while maintaining short exposure times, making the system more tolerant of production environments and larger inspection volumes. Uniform illumination also improves the quality of the reconstructed image by minimizing contrast variations across the projected pattern. The example shown here illustrates a structured light projector that can project interchangeable precision reticles using engineered LED illumination. Different patterns can be selected depending on the application, whether the application is dimensional metrology, robotic guidance, or general surface inspection. In addition, it can be used without a reticle to provide a uniform field for inspection of defects, for example, on large glass panels. Ultimately, improved illumination directly translates into improved measurement accuracy. Grid patterns are only one approach. Another widely used technique provides thousands of individual points. Point cloud projection is particularly well suited for applications involving irregular or highly textured surfaces. Instead of projecting continuous lines or grids, the illuminator projects thousands of discrete points that can be individually identified by two cameras operated in a stereo configuration. Because each projected point can be matched independently, the technique is remarkably tolerant of partial occlusion and performs well on objects with complex geometry. These characteristics make point cloud projection especially attractive for robot guidance, automated bin picking, object localization, optical detection, and many automotive assembly applications. Like the previous example, achieving reliable performance depends on producing a bright, highly uniform, and geometrically stable projection pattern. In both structured light architectures, illumination is not simply enabling the camera, it becomes an integral component of the measurement process. So far, we've been measuring shape. Next, I'd like to shift the geometry to material identification. Structured light reveals the object's geometry, but multispectral and hyperspectral imaging reveals something entirely different, its spectral signature. Every material absorbs and reflects certain wavelengths of light to create its characteristic spectral signature. By imaging beyond conventional RGB, machine vision systems can distinguish materials that appear nearly identical under white light. The example shown here uses near-infrared to identify rocks within a batch of walnuts. Applications range from food inspection and pharmaceutical verification to semiconductor inspection, recycling, agriculture, and biomedical analysis. Hyperspectral imaging captures many narrow spectral bands, making it extremely effective when very small spectral differences must be resolved. Multispectral imaging uses fewer, carefully selected wavelength bands, but for many industrial applications, this approach provides essentially the same decision-making capability with lower system cost, faster acquisition, and simpler data processing. Rather than viewing multispectral imaging and hyperspectral imaging as competing technologies, it's better to think of them as complementary tools optimized for different inspection problems. One of the advantages of LED illumination is that those wavelengths can now be electronically configured. One of the strengths of LED technology is the ability to independently control each wavelength channel. Instead of relying on broadband lamps and mechanical filters, each LED wavelength can be electronically adjusted to provide precisely the spectral content required by the application. Individual channels may be operated independently, combined simultaneously, or rapidly sequenced under external electronic control, as shown here in our example of the LumiSpectra. As a single fiber-coupled multispectral source, it can be used to inspect semiconductor wafers, defects on other materials, or to identify contaminants. This provides tremendous flexibility. The illumination spectrum can be optimized for specific materials, synchronized with cameras, or adapted dynamically as inspection requirements change. Because LEDs switch extremely quickly, multispectral image acquisition can often be performed much faster than with mechanically scanned systems while maintaining excellent repeatability. In many applications, this programmable spectral flexibility enables multispectral solid-state LED systems to deliver the required inspection performance with significantly lower system complexity. Spectral performance is only part of the solution. Illumination geometry is equally important. The geometry of the illumination system has a significant influence on the overall hyperspectral imaging quality. Positioning the illumination at approximately 45 degrees with respect to the conveyor and camera provides a practical balance between maximizing reflected signal while minimizing unwanted specular reflections. Keeping the illumination and camera pupils close together reduces variations in shadowing across the field of view, particularly for objects with significant height variations. The illumination should always match the field of view of the camera as closely as possible. This improves optical efficiency by directing useful light only where it is needed. Careful attention to illumination geometry often produces improvements comparable to increasing optical power while simultaneously reducing glare and improving measurement consistency. These concepts come together in one example of a high-performance hyperspectral illumination architecture. This example illustrates a projection line illuminator on the order of 900 millimeters in length, designed specifically for line scan hyperspectral imaging. Each illumination module is engineered to match the camera's field of view in both length and width over a large depth of illumination, maximizing optical efficiency while maintaining excellent uniformity across the inspection line. Other systems that lack stack illuminators horizontally to form a long line fall short in uniformity, particularly as a function of depth of illumination required for larger objects, such as in the food inspection and recycling industries. Multiple modules can be combined with coincident fields of view to increase the radiance for faster conveyor speeds without changing the overall illumination geometry. Depending on the application, the system may use either direct LED illumination or remote fiber optic delivery. Fiber coupling provides considerable flexibility by allowing the illumination engine to be located remotely while delivering high optical power to compact inspection heads, while direct LED illumination offers somewhat higher intensity but is less compact. Thermoelectric temperature stabilization maintains consistent optical output and spectral characteristics during extended operation, while programmable electronic control allows wavelength selection, triggering, and system synchronization. The overall objective is to provide the combination of high radiance, excellent uniformity, and spectral stability required for demanding line scan inspection systems. Where do these illumination technologies make the greatest impact? Let's look at several representative applications. Throughout this presentation, we've discussed several different illumination architectures. Each has been developed to meet different classes of inspection challenges. In food inspection, spectral imaging can identify bruising, moisture content, ripeness, foreign materials, or internal defects that may not be visible under conventional illumination. In pharmaceutical manufacturing, multispectral analysis assists with coating inspection, composition verification, and pill identification. Within semiconductor and electronics manufacturing, carefully selected wavelengths reveal varied features, contamination, surface defects, and process variations that conventional RGB imaging may miss. Textile inspection benefits from spectral signatures that distinguish different fibers and materials, while recycling systems increasingly rely on spectral information to separate plastics, metals, glass, and electronic waste. Although the applications are quite diverse, they all illustrate the same principle. Choosing the appropriate illumination architecture often determines what information becomes available to the inspection system. Continued improvements in LED technology are opening even more possibilities. Most multispectral and hyperspectral inspection systems today operate within the visible, near-infrared, and short-wave infrared regions. However, continuing advances in high-power LED technology are steadily extending practical illumination further into the ultraviolet. Ultraviolet wavelengths interact with materials differently than visible and infrared light. Some materials fluoresce, others exhibit strong absorption, while certain contaminants and coatings become much easier to detect. For example, ultraviolet illumination is finding increasing use in semiconductor inspection, electronics manufacturing, fluorescence imaging, forensic analysis, and industrial quality control. Although many of these applications are still emerging, advances in LED performance are making ultraviolet machine vision increasingly practical. Looking across the spectrum from the deep ultraviolet through the shortwave infrared, we now have access to spectral information that was simply not available with conventional illumination technologies. That expanded spectral toolbox will continue to create entirely new inspection opportunities. So, where is machine vision heading next? Several important trends are shaping the next generation of inspection systems. Artificial intelligence is rapidly improving defects classification, but reliable AI depends upon consistent, high quality image data, and that begins with illumination. Imaging systems continue to operate at higher speeds and higher resolutions, requiring greater optical power and increasingly precise synchronization between illumination and cameras. We're we're also seeing rapid growth in shortwave infrared imaging, multimodal inspection systems that combine several imaging techniques, and computational imaging methods that extract more information from every acquired image. Adaptive illumination represents another exciting direction, allowing wavelength, intensity, or illumination patterns to change dynamically in response to the inspection task. At the same time, real-time spectral analysis is enabling immediate material classification directly on production lines. Taken together, these developments point toward machine vision systems that combine spatial information, spectral information, and computational intelligence into a single integrated inspection platform. All these systems become more capable. As these systems become more capable, the demands placed upon illumination will continue to increase. That brings me to the main points I'd like you to remember. I'd like to conclude with 5 observations. First, illumination has evolved from simply lighting the scene to becoming one of the primary determinants of inspection performance. Second, higher radiance enables faster production speeds, shorter exposure times, and more accurate measurements. Third, no single illumination architecture is ideal for every application. Structured light, multispectral imaging, hyperspectral imaging, and projection line illumination each address different inspection challenges. Fourth, spectral flexibility provides opportunities to reveal material information that conventional imaging simply cannot detect. Finally, advances in engineered and LED illumination continue to expand the capabilities of machine vision across an increasingly broad range of industrial applications. Ultimately, better illumination leads to better information, and better information leads to better inspection decisions. I'd like to thank you for joining today's presentation. I hope this discussion has provided some insight into how engineered illumination is helping enable the next generation of machine vision systems. If you'd like additional information or would like to discuss a specific inspection application, I'd be happy to continue the conversation.
Thomas, thank you so much for presenting on high radiance LED illumination for high speed machine vision. To everyone that's joining us in the audience, if you haven't already, you can go ahead and type your questions and comments into the Summit chat box. And do not worry, if you have not been answered yet, you will be reached via email at a later date. Thomas, we have a couple minutes here for questions. So I wanted to ask, you mentioned that there are several types of commercial hyperspectral illumination systems that are available today. What are they and how do they compare?
Sure. Well, one of the historically tungsten halogen lamps were the workhorse. More recently, LED lights of various types, including the ones that we demonstrated in this presentation, and also super continuum fiber lasers.
Mhm.
Now, the tungsten lamps have a very smooth, continuous spectrum, and they're relatively inexpensive, but they generate a lot of heat. It's hard to actually, because of their size of the source, image it where you want to have the light on the line, for example, of a line scan system. And they have to be replaced very often. Their lifetime is very short. So they also require continual recalibration.
Mm.
Super continuum lasers are great in the sense that they have a very broad spectrum, very high brightness because they're a laser source, which means that they can be easily imaged with a relatively small lens. However, they're extremely expensive, and for many of the um, um, inspection requirements in the market, they're far too expensive. So LEDs have really come along to fill the gap,
Mhm.
and there's a number of types, but modern LED systems offer the long lifetime, excellent electrical efficiency, very stable output, fast electronic switching, and can be tailored to specific applications. Now, there's no single best solution. The right choice depends on many things, including wavelength range, conveyor speed, working distance, object size, spectral flexibility, and overall cost of ownership. So, for many industrial machine vision applications, engineered LED illumination provides a very attractive balance of performance, flexibility, reliability, and operating cost. And if you'd like to have any more information on that, you can go to our website where we have a link to a hyperspectral imaging webinar presented in 2025.
Many hyperspectral line illumination systems achieve longer illumination lengths by simply placing multiple illuminators side by side. Why do you emphasize projecting a single continuous line instead?
That's a really good question, and it really speaks to the strength of the system we demonstrated. So, many of the LED systems, or even tungsten halogen systems out there, uh, they get the they get the long line field of view by having multiple modules. Each module has its own illumination pattern.
Mhm.
And they do superimpose to some level. But if you move closer or further away from the illumination plane, they're more intense or less intense. So you have peaks or dips in intensity, which are hard to address and can obscure information that would otherwise be observed by a continuous line, as we presented earlier.
I think we have time to squeeze one more in. How practical is ultraviolet illumination for industrial machine vision?
That's a good question. The performance of the short wavelength UVC, UVB LEDs has increased considerably from the microwatts level to tens of milliwatts to even hundreds of milliwatts per LED now. Uh, the real challenge is cost. They're more expensive. The optics, because they have to be UV compatible, are more expensive. However, they offer significant benefits over existing technology that also is in the UV. For example, mercury lamps, which have very limited lifetime, uh, require constant calibration, um, and are toxic. So many applications in fluorescence, looking at contamination, coatings, adhesives, biomedical materials, semiconductor defects can be addressed in the UV with LEDs as they emerge.
Awesome. Thomas, thank you so much for sticking around for a couple extra minutes here to answer some questions. One final note here that this session is hosted by us at Photonics Media, and we certainly hope everyone is enjoying the Inspection Summit. Thank you all so much for joining us.